Okay, so picking back up, let's jump into 4 because I don't want to jump too far in our level of difficulty when we just had a weekend break and, you know. So the top of a 25-foot ladder is sliding down a vertical wall at a constant rate of 3 feet per minute. When the top of the ladder is 7 feet from the ground, what is the rate of change of the distance between the bottom of the ladder and the wall? Okay? So, we haven't necessarily on the others as much, but if you go back to those steps, one of the first things it suggests is we need to draw a picture. Okay? The top of a 25-foot ladder is sliding down a vertical wall. So, here is my wall. Here is my ladder. Okay? We know this is a 25-foot ladder. And we know it is sliding down the vertical wall. Okay? When it's sliding down the vertical wall, we'll talk about what that is here in a moment, but it's sliding down at a rate of 3 feet per minute. Okay? When the top of the ladder is 7 feet from the ground, I'm not going to put that on my triangle or on my figure. When the top of the ladder is 7 feet from the ground, what is the rate of change of the distance between the bottom of the ladder and the wall? So, and I feel like my ladder should be more vertical, but that's all right. Okay. When the top of the ladder is 7 feet from the ground, okay, so that's not the whole time, but when it is, sorry, I have a number in the wrong spot. What is the rate of change of the distance between the bottom of the ladder, so the bottom of the ladder is here, and the wall? So what we're trying to figure out is that change there. Okay? Now, what shape did I end up drawing? A triangle. Huh?
A right triangle.
A right triangle. What connection can we use on a right triangle?
Trig. SOHCAHTOA.
I'm actually not going to, although I will say the SOHCAHTOA, the trig doesn't really come up in my notes as much, but it does come up in homework. So that's one of those you're going to be frustrated about, but keep those in mind. This one, when we don't have any information about angles, but we're talking about all 3 sides of the triangle. What connection do we have with all 3 sides of a triangle? Well, it's a right triangle.
A squared plus B squared equals C squared.
Mm-hmm. So Pythagorean theorem. Now,
Go.
I'm going to call my bottom side X because I'm going to use that for a horizontal distance. I'm going to call my vertical side Y.
This is the 2x dx dt plus 2y dy dt.
Mm-hmm. It is. Now I'm going to get the equation to begin with. And then what do we know about this side? This ladder. Does it change?
No.
The ladder is 25 foot the whole time. So
This
with
is like
that,
a very slow fall. This is a
Very gradual.
so
3 feet per minute.
for my equation, I'm going to use the formula, the Pythagorean theorem, but I'm going to make it x squared plus y squared. I'm going to say equals 25 squared. We don't want extra variables in there that we're not going to have knowledge about. Okay? And 25 doesn't need to be a variable because it's not just when it's 25. It's 25 the whole time. Okay? Now, what's given here? What is this 3 feet per minute that's given?
velocity.
Well, it's a change. It is a velocity. It's a change in what side? It's a change in the side that I labeled as,
Oh, wait.
I labeled mine as y.
Okay.
So if it's a change in side y, I'm going to call that dy dt. Now, what's the other thing? it is sliding down the wall, which means it is a negative 3 feet per minute. Okay. And then it goes on to say when the top of the ladder is 7 feet from the ground. So when? Okay, when the top of the ladder is 7 feet from the ground. Notice I just put in parentheses there because it's not 7 feet the whole time. But that's the time we're going to ask, right? What is the rate of change of the distance between the bottom of the ladder and the wall? So what are we being asked? We're being asked for this change here. What is that change? Well, not number, variable-wise. Like, in other words, if moving down the wall was dy dt, moving out the wall is dx dt. So we're being asked, what is dx dt? What is dx dt when, what do we know? Y is 7. Because that was the provided length they gave us. And that is 7 feet. Okay? Okay. We've got our know, our given, our find, we drew a picture. Let's do this. We have the equation x squared plus y squared equals 25 squared. You need to differentiate. Eli, this is what you were given earlier. We already differentiated this one in the intro, right? Derivative of x squared is
2x
plus the derivative of y squared, and the derivative of 25 squared is 0. Don't fall for the trick of, oh, 2 times 25. Don't fall for it. Okay. At this point, we are trying to solve for dx dt when y equals 7. I'm going to do this a little bit differently in that I'm going to suggest, let's go ahead and solve this for dx dt, and then we'll plug in later. I've shown you where you plug in and then solve. I'm going to do this one where we're going to solve and then plug in. So
dx dt would equal negative 2y dy dt over 2x. I think there's 2's to factor out technically.
okay. I wrote mine as negative 2y divided by 2x times dy dt. It's the same thing. I do agree with Logan's comment that those 2's can cancel. Don't lose track of the negative. Now, officially, we are trying to find dx dt when what? Y equals 7.
Yeah.
Do we have all the information we need?
No.
What are we missing?
X.
Okay. Because we know dy dt. We know y. We don't know x. At the time when y is 7, what could we find about x?
We could just use 7 and then
Hypotenuse will be the same, 25.
Hypotenuse is always 25. So if the hypotenuse is always 25, at the moment y is 7, could we find what x is at that same moment?
Yeah.
Yes, because that right angle is going to be there between the wall and the ground at all times. So we could say x squared plus 7 squared equals 25 squared.
what's 25 squared?
625. So x squared plus 49 is 625. X squared equals 576.
And that is, isn't it 24?
It is 24. Square root of 576 is 24. Now do we have everything we need to plug in?
Yep.
Now, don't forget the negative. As I agreed, the 2's can cancel. Negative of y is 7 over x, which is 24, times dy dt, which is negative 3. And I made it negative 3 over 1.
It's going to be about 7/8.
I personally would cross cancel because that's the type of person I am. What did you say? You said 7/8?
Yeah.
Okay.
You get, well, whatever, 24.
7/8 what?
Well, it's probably going to be change of the distance. It'd be feet per minute, right?
It would be feet per minute. And here's how I know is it's feet per minute, dx over t. X, y, all of this is being measured in feet. Time is being measured in minutes.
Well, I should just look. It said what the rate of change of the distance, so that would mean the direction of the distance.
Okay. How do we do?
Time.
Someone okay? Okay. 5 is a really good one to look at, but we're going to skip over to 7. As I don't even know if I'm going to be able to get to 8 at this point. And 8's a good one too. You guys know you can find these in the answer key. I can't guarantee they're in the video from last year because every year I have to skip around in this lesson. They might be though. Okay. An inverted cone is leaking water at a rate of 1 cubic centimeter per minute. The cone has a height of 9 centimeters and a diameter of 6 centimeters. Find the rate at which the water level is dropping when h equals 3, given that volume is 1/3 pi r squared h. So they were nice. And I do feel like these type of formulas are technically usually given. We are going to know 1/3 pi r squared h. Okay. We're going to draw a picture. Inverted cone, aka upside down cone. What do we know about this cone?
Height of 9 centimeters, radius of 3 centimeters. Losing water in a cubic centimeter per minute.
Height is 9 centimeters. Radius was what? Oh, wait. Technically,
What?
diameter is 6 centimeters.
The radius is 3 centimeters.
Which, yeah, my brain, because they told us 6, right? Yeah. So thus, we know radius is 3 centimeters. What about the inverted cone is leaking water at a rate of 1 cubic centimeter per minute? What is that?
The volume decreasing per minute.
So that is dV dt. It's a change in volume over time. And it's leaking water, so that's going to be a negative 1 cubic centimeter per minute. And what do they ask us to find?
Find the rate when the height is 3.
Okay, what rate when the height is 3? Okay, so if we're finding the rate, so it's d something,
AV dt.
What is water level? What are they referring to there?
Depth.
Depth. What's a better word for depth in this that goes with this formula? Height, right? We got to keep it all in terms of V, R, and H. If it's not V, R, or H, we've got to translate it to V, R, or H. Fair? Because that's what's in my formula. So we're going to be looking for dH dt when H equals 3. Now, before we go any farther, we have an issue. Okay? We've gotten all the information we can from the stem of the problem. We've got our formula. We know dV dt. We're being asked to find dH dt when H equals 3. We have an issue. When I go to differentiate this, I'm going to get a dV dt because there's a V. I'm going to get a dH dt because there's an H. And I'm going to get a dr dt because there's an R. I'm given dV dt. I'm asked to find dH dt. Did we ever mention a change in radius? Did we ever mention dr dt? We mentioned a value for R, but we never mentioned dr dt. So that is a problem. When you notice that there is no info, and in this case there's no info on dr dt, we have to do something differently before we proceed. Usually in this scenario, and this is what we're going to look at, there is a way to take this R and define it in terms of another variable. And in that case, this means we have to define it in terms of H. Okay? So what we're going to do then is, I'm going to put it here, we're going to define H in terms of R. Okay? Or wait, reverse that, R in terms of H. My apologies. The idea is we don't have a dr dt, we need to get rid of R in the formula. To get rid of R, we're going to turn it into H's. Okay? I reversed the way I said that. Now, with that in mind, okay, we have this cone here. And somewhere here, the water level is dropping, right? Obviously, that's not a set amount, but that is changing. And what we can do, we have H of the whole big cone. We have the height of the whole big cone. We have the radius of the whole big cone, yes? With that height and radius, I don't know if you guys can see it or not, but with that height and radius, I can create a right triangle. Okay? This is a right triangle right here. So I know I have a right triangle that has a height of 9, a radius of 3. Now, that's the whole cone. My other right triangle comes wherever your water level is. Now, is there a set height for what the water level's at?
3.
Well, but is it always at that?
No.
No. It varies on the problem. So this here, I'm going to call, I believe I usually just call them H and R what they are. Yeah. I'm going to call this H and R because that height and radius are changing as the water level changes. Yes, as my water level keeps getting lower, those are going to change. So now we have a secondary smaller triangle. That's a right triangle that has an unknown R and an unknown H. I feel like this is taking us back to middle school math. Do you see a pair of similar triangles here? That's what I've tried to create. Pretend that my drawing is perfect, right? There's a couple of similar triangles here. And so the idea is that, I don't have the right mathematical lingo off the top of my head, but the idea that similar triangles have proportional sides. Proportional angle, or same angles, proportional sides.
Ratio, that's it.
Yeah, so we can set up a ratio here, a fraction equal a fraction. Now, I don't know which way you guys remember setting this up. I'm going to throw a couple out at you. I could say R over H is equal to 3 over 9. Or I could say R over 3 is equal to H over 9. So we could say the radius of the small triangle to the height of the small triangle is equivalent to the radius over height of the big triangle. Or you could go, what I did here, radius from the small to radius of the big. Height of the small to height of the big. Lots of different ways we could do this, right? Now, any way you go about it, we need to solve this for R. Do you remember you can also do cross products? And here's the deal. If you're setting it up and like, I don't know if I have a right way, are your cross products the same? Any way I set it up that's correct, I'm going to have 9R equals 3H. Okay? Do you guys have a tendency towards one or the other of these?
The first one, probably.
The first one for you? I mean, to me, I've taught them both over the years, so usually I feel like there's a tendency, but so here you could say that 3/9 reduces, yes. We could say R over H equals 1 over 3. You could cross product it, or how do we solve for R? Because we want to define R in terms of H. R is going to be equal to what? 1/3 H. If it's R divided by H, we can multiply the H over. You can say R is 1/3 H, or if you prefer, you can say R is H over 3. 1/3 H works for me. Okay, guys, here's what we need to do. We need to take our formula we were provided, 1/3 pi R squared H. Do not differentiate yet, because if we differentiate, we're going to have a dr dt, and we don't want that. We need to get rid of the r. So replace r. 1/3 pi, what am I putting in for r? 1/3 h, quantity squared, times h. Clean this mess up. What is 1/3 h squared?
1/9 H squared.
Okay, 1/9 h squared. What's the 1/9 times the 1/3 out front?
It'd be 1/27.
Okay, and that's 1/27 times pi. How do you feel if I say pi over 27? Or 1/27 pi.
Yeah.
Either way. H to the what? Third, because h squared and h to the third. So we just took our volume formula and we rewrote it in terms of h for this particular problem. Now when I differentiate it, I'm not going to have a dr dt thrown in there to mess with. Are we making sense here? Okay, I mean, we're at the more complicated level, obviously, right? Okay, let's differentiate. dv dt, what's the derivative of pi over 27 h cubed?
3 would be pi over 9
Thir-
h squared.
Mm-hmm. And then the part you didn't put on the end, but yeah. 3 times pi over 27 becomes 3 pi over 27, which does reduce to pi over 9. H squared when you subtract 1 from your power, and then times dh dt, because we took the derivative of an h term. Okay. We know dv dt. We have an h we can plug in, and we're trying to find dh dt. We're ready to plug it all in? dv dt is what? -1 pi over 9 times because we're at the end and we're solving it out, now you can put in h equals 3. So 3 squared times dh dt.
So it's gonna be just gonna turn into pi. So then it's just gonna be dh dt equals pi. Or negative 1 over pi.
Yeah, because 3 squared and 9 end up canceling, so you just have pi. Negative 1 divided by pi is negative 1 divided by pi. What kind of label are we going to have here?
Centimeters per minute.
Okay.
Centimeters cubed per minute.
No?
No, centimeters per minute.
Always look at what your original was. It was, or what we were trying to find. We're trying to find the HDT. The change in height. Height is just going to be measured in a plain old centimeters over minutes, which is, or over time, excuse me, which is measured in minutes. Okay? I have, for whatever reason, a decimal answer here too, but I don't think you'd ever be expected to do a decimal answer in this problem because this right here, that's a beautiful non-calculator problem. As much as we want to grab for the calculators, we didn't really need them there. Maybe there's times you want them, but it's doable without a calculator. Okay? So, watch for those. That's going to happen when you have a variable missing like that. And the other one I really wanted to look at was 8a. It's the shadow problem. You're going to...
It's not like we can come in and homer the next 2 days.
I know, that's the problem. That's the problem. And here's the deal. They have the picture here. I don't know if you guys are seeing it or not, but there's 2 triangles happening here. Do you guys see the 2 triangles? There's big triangle with the lamppost, and there's small triangle with the guy walking away from the lamppost. So that's what you're going to be looking at here is a big triangle and a little triangle, that those again are similar triangles. Okay, but that's actually how you're going to create your formula here. What do we know? A lamp post is 26 feet above the sidewalk. Does that lamp post ever change height?
No.
No. So I can confidently put that 26 on. Andy Great, Andy Great, she likes to do that, is a 6-foot tall calculus teacher. So not me. And is walking away from the lamp at a rate of 4 feet per second.
That goes on both, doesn't it?
When he is 20 feet away from the lamppost, find each of the following. So this is when x equals 20. Is that x always going to be 20? No. In fact, I probably shouldn't have put it in there because that's going to get a confusing piece there. Okay? So you know in the big triangle, this is a 26. In the small triangle, this is a 6. I believe what I do is I call these x and y. Okay. The formula to set up. Okay, we're doing this one a little bit differently because I'm just trying to get you some pieces. Oh, wait. I labeled these wrong. This is not x and y exactly. One of them's right, one of them's wrong. 6 and y is 6 and y. What did I screw up here? It's 26 and not just x, but x plus y. My screw up. Okay. Now, with that in mind, can you set up, for instance, 26 from the big over 6 from the small equals x plus y from the big over y from the small. That's kind of your setup you can look at there. Okay? Hopefully that gives you a little bit of an idea there. You can clean that up, get an equation out of it. Yeah. Here's what I need you guys to do. Do the homework to the best of your ability. Go through